All right, so let's start the second half. So welcome back. We're going to start the second half of Brendan Hassan's talk on rationality of twisted moduli. So please take it away, Brendan.
Thanks so much. And so I wanted to talk about some basic properties of these twisted moduli space before I get too deep into the rationality. So the first set of basic properties, which I can't claim that much credit for, so this is foundational work of Duncan Reichstein and additional follow-up in the case of moduli space by Florence and Reichstein. And so the first thing I want to point out is that, in fact, these moduli spaces, they're never pointless. They always have rational points, no matter how you choose the representation. And in fact, the second statement really is much stronger than the first. Not only do they have rational points, but they're indeed unirational over the ground field. So these are good varieties from the perspective of arithmetic geometry. You have unirationality. And so let me say a little bit about why these are true. So I basically gave the argument already for the case of 4 points. And so let me just sort of tell you the high points. So we're going to take the spec L, which is a degree n extension with the prescribed Galois group, and I'm going to embed it, as we've seen before, into a projective space, but not Pn minus 1, but a Pn minus 2. And so again, this is using the elements of trace 0. So let me just remind you. So here we're taking trace 0 elements. And so this gives us, as we've seen before, a configuration of n points in Pn minus 2 in linear general position. I think I have a picture. So yeah, so here the red points are the points specified. So I guess in this picture, we have 5 mark points. And so what I like to do is I'd like to take some random point in Pn minus 2. And let's choose it to be sufficiently general. And so there is a unique rational normal curve through n plus 1 points in Pn minus 2, provided they are in linear general position. And so I take the rational normal curve, C, and so this rational normal curve is contained in Pn and contains the spec L and the point P. And the great thing about this construction is that the rational normal curve is unique. So I don't care about whether the individual points are defined over the ground field. As long as the whole cycle is defined over the ground field, the Castelnuovo's arguments give us a unique curve through those points. It's all essentially linear algebra. And so what I can do is the map that assigns to this point in Pn minus 2, namely the point P that I specified, to the element of moduli space, this is a dominant map. And so this shows that this Pn minus 2, which is of course rational, admits a dominant map onto the moduli space of n points twisted by rho. And this gives unirationality, and it gives a rational point over a reasonably large field. In fact, if you pass to the compactification, you can always get a rational point. Over small fields, you might not have rational points for given representations. For instance, if you look at M0n with a trivial representation and n is larger than the cardinality of the field, you're kind of out of luck. But the compactification is fine. So this is the argument. Now, there's sort of a more moduli theoretic way of spinning this, which is important. So this classical argument has been explained in somewhat more modern terms by Kapranov, the Kapranov blow-up construction. And this Kapranov blow-up construction can be interpreted as itself a moduli space of pointed curves, n+1 points now, where one of the points is fixed. And the map here that I described, the dominating map, is really just a forgetting map. And so the reasoning is that once I have this rational point, this moduli space becomes rational to Pn+2. And so this gives a nice corollary. The corollary here is that for all odd n, M0 n rho cross P1 is actually rational. So this comes out of this reasoning here. So basically the idea here is that by breaking symmetry, by taking this n plus first point and calling it out specially, it gives you some rationality straight away. And then the forgetting maps give you some stable rationality. And so let me say a little bit about why this is true. So this phi n+1, the forgetting map, is in fact a P1 bundle in the Zariski topology because of the standard fact that every genus zero curve with an odd degree cycle is isomorphic to P1, essentially the one-dimensional version of the Springer theorem. So this is why the universal family over the moduli space can be interpreted as a P1 bundle rather than as an étal bundle. An étal P1 bundle. This is a Zariski P1 bundle. Okay. A nice corollary to this is that even if you just have an odd orbit, so if n is even, but say if it partitions into an orbit of length 3 and an orbit of length 9, that's enough to get the stable rationality. So you don't need an even number of points. You just need you don't need an odd number of points. You just need to have an odd orbit. Well, maybe let me just write this here. So you don't need odd n for stable rationality. So this is a little bit stronger than a previous result. So Florent and Reichstein did consider this problem over infinite fields, and they showed over infinite fields that M0 n rho is rational for odd n. But the statement I have here at the top, when you have an odd orbit, the stable rationality is new. And so Florent and Reichstein didn't consider stable rationality as much. We're more preoccupied with that. So this is a consequence of just looking at these classical moduli space constructions. All right, let me talk a little bit about other results that that we know how to prove, and I'll see how much I can get through. So there's more in our paper than I think I can really cover in the time that I have, but let me talk a little bit about what we know how to show. Even over finite fields, M0 n rho is always rational, provided that the number of points is odd. And so this is valid even over finite fields. Over the real numbers, these twisted moduli spaces are always rational. And finally, if you have a sufficiently large number of points, n equals 2m points, but you need to have at least 6. And if the field K admits a biquadratic extension, then there exists a choice of rho such that M0, 2m rho is not stably rational. And let me just emphasize that this is the best possible This is the best we can do. Because I showed to you that if I have 4 points, it's always rational. And so 6 is the first case where we can hope to show that there would be an example that is not rational or even not stably rational. So this sort of complements the construction I gave early on with the conics and the 4 points in the plane. One kind of vexing open problem that I think deserves some attention and probably some computation is, suppose that you're in a situation where the Galois representation is cyclic. So that, I mean, let's say it's an n cycle or a product of cycles. You don't want to have any fixed points, but it could be a product of a 3 cycle and a 9 cycle. Can it be that the moduli space is irrational? And so, for example, over a finite field, are there any twists of moduli that are irrational? And as far as I know, based on the computations that we've done, I don't know of any examples of moduli that are irrational. I haven't tried really hard looking for them, but I haven't seen any examples. And so this is something that is a sort of a vexing problem for us. We should probably look at more data. It's certainly computable whether there are topological obstructions to or cohomological obstructions to rationality in these cases, but we have not found any. We've spent a little bit of time looking for them. And so the last thing I want to mention is that, so suppose you're in a situation where you have a pair of points that are left invariant under the action. I don't insist that the points be fixed. They can be permuted by the action, but I want to have a pair of points that is invariant under the action. And so then there is an algebraic criterion for when the moduli space is stably rational. And for the people who are torically inclined, this is basically because we have a toric variety. We're in this situation. And so I'll talk, if I have time at the end, I'll talk a little bit as to how you give the toric construction in this case. But since, give me a moment. My security locked me out because I haven't, see if, sorry about that. Okay, my apologies. So you get a toric variety in this situation. And let me say a little bit more about how these results are shown. And this will give me a chance to all right. So let me remind you what the first statement of the theorem is, that the moduli space M0 n rho for any representation rho is rational for odd n. And so let me tell you a little bit about what goes into this. Okay. So the key ingredient here is the Gelfand-McPherson correspondence, which is getting a little closer to the spirit, I think, of the Schubert, the Schubert seminar. So let me just remind you of this in case you haven't seen this before. You look at the 2 by n matrices, and on the one side, you let GL GL2 act, multiplying by the left. On the other side, you let the diagonal matrices act, multiplying by the right. And these left and right actions, of course, commute with each other. And so we can, we have both groups acting. The multiples of the identity on each side act more or less the same by rescaling both factors. But other than that, these actions don't really interfere with each other. And so this is a construction that we want to use. So when I take the matrices and I look at the right action by the diagonal matrices, if I insist that none of the columns are 0, what I get here is actually n copies of P1. Each of the columns gives you one copy of P1, and so as I take all the n columns, I get P1 to the n. On the other hand, I can focus on the GL2 action of the matrices from the right, and if I insist that the rows are independent, I can use the Plucher relations to give that the quotient is the Grassmannian. And I think, yes, so this is what I want, that the Grassmannian is a quotient of the matrices by the GL2 action. And when I put all this together, I get that the quotient of P1 to the n by the diagonal action of PGL2 is realized as a quotient of the Grassmannian by the action of the maximal torus. And for those of you that are keeping track of linearizations, I can do this compatible with linearizations on both sides, but I'm not going to dwell too much on that. Now, another nice aspect of this is that if I look at, let me go back to the original construction. If I look at these 2 by n matrices, I could permute the columns of the matrices. I have n columns, so I can permute them. And of course, there's a typo here, because I meant permuting the columns. My apologies. And so when I permute the columns, there's a symmetric group action on the columns, the n columns. And so I can use that symmetric group action to get a presentation of M0 n rho as a quotient of the Grassmannian G2n by a torus T, where this T is a twist of the diagonal torus associated with this Galois action. So I'm taking a diagonal torus, but one for which the characteristic polynomial is gives you an interesting Galois action, and it's not so hard to produce for any Galois action that you have over the field. You can find a polynomial that has that characteristic. And so these twisted moduli spaces are quotients of Grassmannians by twisted tori. All right, and so now suppose that we have an odd number of points, so n is equal to 2n plus 1. And so then I am looking at the Grassmannian, which has dimension 2 times 2m minus 1. The torus has dimension 2m. And now I want to use a computation that, well, I learned it from Kliatchko, maybe it's older. So if you have a 2m minus 1 dimensional, let me just address that, 2m plus 1 dimensional vector space, by apologies. And then you have the generic orbit for the action of a maximal torus on that Grassmannian. And then you look at a subspace, W, of their space V that has codimension M. This subspace gives you a Schubert cycle. So the Schubert cycle being the subspaces of V that arise from W. And then the assertion is that when I take X and intersect it with the Schubert cycle, I get 1. And so this is quite remarkable. So I don't really understand conceptually why this is the case. And probably one of you can explain it to me in a way that will be transparent. But it's a beautiful calculation that this gives you the right answer. And so here I am living up to the Schubert challenge. So the Schubert calculus allows you to show that these torus orbits, that you can sort of find some Schubert class that meets them in exactly 1 point. And so the corollary here is that when I look at this mapping from the Grassmannian into the quotient on the torus action, so this is the Grassmannian of 2-dimensional subspaces in a 2-dimensional space, and then I mod out by this maximal torus. This has a rational section that's isomorphic to a Grassmannian of smaller dimension. Namely, this is the Gur2W. And so the nice consequence of this is that the moduli space, and let me just remind you that the moduli space that we are focused on was a quotient of the Grassmannian by this maximal torus. But this Schubert calculation gives us that the quotient is actually rational over K. And so this is one way to see that these moduli spaces, twisted pointed genus zero stable curves, they're always rational, provided you have an odd number of points. One nice aspect of this geometric argument is I used genericity in many places when I was sort of telling you the story, but with a bit of work and a bit of analysis, I can do this with over even small fields. So I can find transverse slices, appropriate W's that work even over fields that are pretty small, finite fields. And so it's nice because you can make this argument work even when M0 n rho has no FQ points. You can still show it's rational. It's just kind of fun. The compactification has many points, but the moduli space itself might not have them. Okay, so let's see how I am for time. I'm sorry, this went faster than I thought, so let me do one of the other arguments. And so let me focus on argument 4. And so here we have a map from the symmetric group. From the Galois group to the symmetric group on n letters that preserve a pair of points. Say the last 2 points. And so then I want to show that the corresponding M0 and rho is toric for a non-split torus. And so this will allow us to look at the rationality using techniques from Galois cohomology. And so the key construction that makes this work is the Loss-of-Manning construction. And so let me review this in the split case. And so, as we've done before, we break symmetry. And so we take p n minus 1 and we send it to 0. And pn, we send it to infinity. And then what we want to do is we interpret m0n as a subvariety of the multiplicative group, the n minus 2, modulo diagonal action. And so here what we're doing is we're just taking pn minus 1 to 0, pn to infinity, and everywhere else wherever it goes. And so so we're basically pn minus 1, pn, and then I'm using a projectivity to take it to the points 0 and infinity. And then the other points, say p1 through pn minus 2, they go wherever they go. And so this gives you a realization of m0n as a quotient of gm to the n minus 2 by gm. So you can use the gm here. So this sort of rescales all the variables. And so then over a non-closed field, we let T be a one-dimensional torus. Controlled by the action on n minus 1 through n, and let's let S be an n minus 2-dimensional torus. Controlled by the action on the first 2 points. And then using these, we get a twisted version of this identification star, namely that m0n is contained as a dense open subset of Gn minus 2 modulo Gm. And so we get a version of that. And so then this gives it that for all these, so all the resulting moduli are toric for an explicit torus action. And then Galois cohomology gives the criterion for stable rationality. In other words, the Picard group should be stably permutation. And so one thing I've not done is to try to classify when this reasoning goes through for what kinds of torus actions. I think it might be interesting to identify situations where it is stably permutation, but maybe not actually permutation. Okay, so I think I have come to the end of my time, and so let me stop there and see if there's any questions. Thank you so much.
Thank you. Thank you very much, Brandon, for a beautiful talk.